Hello, this is the Physics FRQ number 2 mastery project for Unit 6. A moon is moving clockwise in an elliptical orbit around a planet. Points A and C are the locations where the moon is closest and furthest from the planet, and point B is equidistant from point A and C. The distances from the planets to the points A, B, and C are RA, RB, and RC respectively. For A, it says in figure 2, draw arrows to indicate the direction of the moon's velocity at both points. Now A, the velocity is going like this, and then B, the velocity is going like this. This is the velocity at this exact single point. Now for A2, in figure 3, draw arrows to indicate the direction of the moon's acceleration. Now, they're both going towards the planet, which allows it to keep in orbit, so that's why it is going towards the planet. Next one, starting with the conservation of angular momentum, providing the expression for the moon speed VB when it is at point B. Okay, so angular momentum Li is equal to LF, and then we want to, the initial angular momentum is RA times the momentum of A, which is momentum is just as times velocity, so we just simple it out like that, and then it should end with RB, oh my god, MB, VB, but we have to add in a sine theta because we need to get the perpendicular component of the the perpendicular component. This is already perpendicular, as you can see here, so that's why we don't need it. And now the mass stays the same, so we can cancel out the mass. So now we have RA VA is equal to, now RB says right here it's just 5 over 2 RA. So we can cancel out this. Now we have VB is equal to 2VA over 5 times sine theta. Now due to the 3, 4, 5 right triangle, sine theta, and theta here is 53, is 4 over 5. So we can plug that in. 4 over 5, so it cancels out the 5's, and then this cancels out, and we have VA over 2. Then part C, on the axis, sketch a graph of the moon's kinetic energy as a function of its distance r from the planet. Now here we have Ka is equal to this, and we have to notice here that this VA is squared, so that means as the radius increases, the velocity decreases as well, but the decrease will be squared, so that means it curves like this. And the reason why it doesn't touch 0 is because it stays in orbit. If it hits 0, then there would be no orbit. Now part G says, indicate where the graph you drew in part C is consistent with the velocity and acceleration indicated for point B in part A. Now part A was this, and the question was, true in part C is consistent. Okay, so as you can see here, the velocity remains positive the whole time. But as you can see here for the acceleration, if we break this up, we can see that there's a negative horizontal component to the acceleration at point B compared to point A. This means that as the radius increases, the acceleration turns negative and makes the velocity decrease as well. And that is consistent with parts here, see that as the velocity decreases, the kinetic energy will decrease as well, which is shown here as the radius increases. And part A shows the acceleration. Okay, thank you.